6.1 is the inner product, length, and orthogonality of vectors. So the inner product will probably be familiar to most students in the course. This is going to look like the dot product, as it's called in physics and oftentimes in multidimensional calculus. Once we have a dot product, we can discuss what the length of a vector is. We'll call that the norm sometimes, or the magnitude maybe even. And then orthogonality is the idea of perpendicularity. And we tend to use the word orthogonal rather than perpendicular in linear algebra. So to get started, for vectors u, v, and rn, we often regard them as n×1 matrices. When we do that, it makes a convenient way to define the dot product that we're already possibly familiar with from another course. If not, this is a nice ground up approach to it. So u is an n×1 matrix, and v is an n×1 matrix. Now, if we transpose u, and we take an n×1 matrix and turn it into a 1/n matrix. So an n×1 matrix, or 1/n matrix, times an n×1 matrix, the dimensions match, so we can perform this multiplication, ends match, and we end up with a 1/1. Well, the 1/1 matrix we'll just typically refer to or write as a scalar. So there's our idea of matrix multiplication between two vectors u and v, which are both n×1. We have to transpose one in order for it to be well defined, and that's the first one. When we do so, we get a scalar out of that. So that's the idea of defining the inner product, and we'll see that it'll match all of our notions of inner product that we might have coming into this. So we define the inner product u dot v as the product u transpose times v. Now note that we don't get that backwards, right? If you do u times v transpose, that's an n×1 times a 1/n, and we're going to form an n/n matrix if we do that. So you really want to be careful with the dimensions. But you'll see that if you've got any experience with the dot product, you'll find that the inner product is exactly the same as that. So we're asked to compute u dot v and v dot u for the two given vectors u and v in this example. So u dot v, I'll write it down as exactly as we've defined it. And I find that that's u transpose times v as matrix multiplication. So a 1/n, or 1/4 times a 4/1. So here's my 1 row, 4 column by 4 rows, 1 column. And I should get a scalar out of this when I'm done. I have 1 times 6 plus 0 times 5 plus -2 times 3 plus 4 times -1/2. And we see all of that written to the right as 6, 0, -6, -2. We add all of those up and we get -2. Now we don't have to write this transpose and this matrix notation every time. It's good to know that that's in the background, and we might use that in more conceptual situations. But typically we're just going to take the dot product the way that we're used to doing it. So if in fact you've seen the dot product before, it's essentially the same as the inner product for this course. So v dot u, rather than writing v transpose u, which would come out to the same value, I'm just writing this down in the way that we know to do it. We take first components times each other, plus second components times each other, plus third, plus fourth components times each other each. Now, we add all these things up, right? And we get -2 again. We get the same value that we got for u dot v. Now notice I did reverse the order so that I matched my v components in the first multiples here, just to be very careful, but it'll turn out that the dot product, or inner product I should call it, as that's how we've defined it, our inner product is actually commutative, and I'll show that on the next page. So not only is it commutative, given by this line here, which is good news, not everything's commutative. Remember that matrix multiplication is not, but we get this for the inner product, so that's nice. But not only is it commutative, but we get distributivity, which is this line. We get associativity of a scalar constant and the dot product. So if we can multiply u by a scalar c and then take the dot product, or we could take the dot product, then multiply that by the scalar c, or we can multiply v by the scalar c and then take the dot product of u with that vector. So none of these make a difference as to what the value actually is. And then an interesting fact, u dot u is always greater than or equal to 0. If it is equal to 0, well, the only way that can be the case is if u is actually the 0 vector. All of these are pretty quick, straightforward to prove. I do the first one. We let u and v be an Rn. Then u dot v is equal to u transpose v, being very formal about everything we've defined. What that looks like is this 1 by n times n by 1 matrix product. And when I carry that product out, I have this sum of multiples here. These are multiples, these are real number multiples, u1 times v1 up through un times vn. So I can commute them. I can write the v entries first, v1, u1, all the way up to vn, un. That's using commutativity of multiplication of real numbers, property that we know exists, right? That we have already. And then I can sort of pull that back out as n by 1 times 1 by n, or sorry, 1 by n times n by 1 matrix products. And I realize that this is actually v transpose times u, which is definition of v dot u. So I've gone from u dot v to v dot u, and I use commutativity of real numbers to show that my commutativity for, or the commutativity property for inner product actually holds. So remember to be very careful in proofs of fundamentals like this. You don't want to just skip from maybe this step to this step without showing the details of it, because it doesn't show that we actually leverage the fact that we know that real number multiplication is commutative in this step right here. If we jump from this step to this step, we're really missing some details in that proof. So it's sort of an incomplete proof. Okay, and the rest of the results in this theorem follow more or less in a similar fashion. Now the length, or sometimes called the norm of the vector v, or maybe even the magnitude of the vector v, is the non-negative scalar, denoted double bars v, kind of like absolute value bars, but double just so we know that we're talking about vector magnitude or vector length. And that's defined by, well, it's the square root of the dot product of v with itself, or the inner product of v with itself. Equivalently, or maybe not quite equivalently, if we take the positive square root when we solve for this equation, then it's equivalent. But we also have this fact. We'll denote the norm squared as the dot of v with itself. Notice that, like we saw above, that's always going to be positive. So it's a reasonable choice to make. Now, let's have a look at the norm of some vectors. So if we take a vector and divide it by its own length, its length is going to, oh, sorry. First off, a vector with length 1 is called a unit vector. That's an important definition to make, right? Unit vectors are commonly used. If you've taken a physics or multidimensional calculus course, you've dealt with unit vectors, vectors that have length 1 already. Now we can turn any vector into a unit vector by dividing that vector by its magnitude. And this is called normalizing the vector v. So let's prove that if we do this, if we take v and divide by its magnitude or its norm, then we'll get a vector whose magnitude or norm is 1. So in this case, we're finding the length of the vector v that's been divided by its own length. So writing down what that means, the norm is the square root of this vector dotted with itself, as we see here. Now remember that these two values are scalars, so we can multiply, we can factor them away from this dot product. So we can factor the scalars 1 over norm of v out to the side. There are 2 of them, so we have 1 over norm of v squared, and then what's left is just v dot v, this inner product of v in itself. Now this is 1 over this norm squared, so this comes out of the radical as 1 over the norm of v, and underneath the radical we have v dot v. Well, square root of v dot v is the norm of v. So we replace that there with norm of v, and then we have 1 over norm of v times norm of v, and we get 1. So now we know that any vector that we divide by its own length is now a unit vector. This proves it for any such vector. The only vector we can't do this with is the zero vector. There's nothing we can multiply the zero vector by in order to normalize it. We're just always going to get the zero vector. So we're asked to normalize the given vector and then confirm that the result is indeed a unit vector. So we take u, take its norm first. So that's u dotted with itself. That's pretty easy to just go through and take each of the entries of u and square them. Okay, that's pretty straightforward situation. We could have written square root of u dot u underneath here, but that's u dot u is just squaring each of the elements of the vector, adding them all up. Underneath the radical, we get the square root of 25, which is 5. Notice that we're always taking the positive square root. This is a length calculation, and by definition, we use this positive square root for the length. So anyway, we have the length 5. Now we divide the vector u by 5 in order to come up with its unit vector v here. And when we divide a vector by 5, well, we just divide all of its entries by 5, and we end up with this unit vector. Now, we could check that this is actually a unit vector by calculating the norm of v. And one way to do that is, well, the norm of v is the norm of 1/5 u. And we can factor this scalar 1/5 out. This is sort of the lazy person's check of this, right? 1/5 comes out, we're taking the norm of u. We've already seen that the norm of u is 5. So 1/5 times 5 is 1. That's again, like I said, that is the lazy check. We proved up here that this is always going to work. So as long as we trust that we found the correct length of this vector, then we don't really need to check this. What we could really get into the details of is squaring this, plus squaring this, plus squaring this, plus squaring this, summing all that up under the radical, taking the square root, we'll find that we do get the value 1 if you carry that out. So second example down here is to let S be the subspace of R3 spanned by the vectors u equals 1, 2, 2 and v equals 3, 0, -1. Find a set of unit vectors which form a basis for S. So a set of unit vectors that form a basis for S. Well, this is a basis for S as is. They're just not unit vectors. So all we have to do in this case is convert them into unit vectors. And note that a unit vector u for this vector u is parallel to u, right? U is, that's the one key concept to keep in mind here, is that if we take u and divide it by its length, it's still parallel to u, right? It's a scalar multiple of the vector u. So it doesn't change the direction of u, it just scales the length of u. So we still have the same spanning set, right? This is just a change of the representation of each of these vectors, but the directions are preserved. And that's what a spanning set really gives, is a set of directions in the space that we're talking about, or the directions of vectors in the space in order to span that space. So all we need to do in short here is to calculate, or is to normalize each of these vectors u and v and write that in the span. U's length is root 1 plus 4 plus 4. So all I've done is gone through and square each of the entries of u. I get square root of 9, and that's 3. V's length is the square root of 9 from 3 squared plus 0 squared plus -1 quantity squared. And I get 9 plus 0 plus 1, square root of that, and that's going to be root 10. So for my vector u, I divide all of my entries by 3 to get this one. For my vector v, I divide all my entries by root 10, and I get this. Each of these vectors are now normalized. Each vector has length 1. We could check that by calculating the norm of each of them, or the length of each of them. And I've written that as a basis set. B is equal to the set of vectors, well, these two vectors, which are the normalized versions of our original spanning set. So that's a normal basis for S. Next up, find the distance between, or we'll calculate the distance between a vector u and v. Well, we define that as the length of the vector u minus v. So we think about it, what u minus v is, if we're given just geometrically, though we don't do a lot of geometric arguments in this course, this might be a decent moment to stop for that. If this was u and this was v, the distance between these two vectors, well, we want to know what this vector is, what the length of this vector is right here, right? Remember that, maybe I should put my arrow going the other way. This is, nope, I think I had it right the first time. This is the vector u minus v. But at any rate, the magnitude of it, so the length from here to here, is the norm of this difference. And it doesn't matter if we do u minus v or v minus u, we're going to get the same value within that norm. So the vector representation is, we don't have to be as careful with that. So that's why this comes about. We take the norm of the difference of two vectors in order to find the distance between them. So this will be similar to the distance between 2 points in space. And we'll draw a comparison to that at the bottom of the page for 2 points in the plane for the Euclidean distance formula. So we're asked now to compute the distance between vectors u and v here. So we just implement the formula. It's the norm, the distance of these two vectors is the norm of the difference of the two vectors. So vector subtraction here, combining these two vectors to that minus sign gives us this vector, -5, -5, -1, and this is actually, I just saw a mistake here, -4 plus 2 is actually -2. So this line here is actually going to be a 4. Now we square each of these entries and add them up, right? This is our norm calculation. Or in other words, we dot that vector with itself underneath a radical. And what we have is 51 plus 4 is 55, and this should actually be root 55 under the radical. So it's as simple as that. And what we'll notice is that this is really, if we were to write these terms out a little more carefully and put it all under the radical, we would see that the structure we have for two vectors u and v and Rn, well, here we are being careful with that. It's the norm of the difference of these two vectors. So I've done my entry-wise differences for u minus v as vectors. And then when I take the norm or the length of such a vector, it's this entry squared plus the next entry squared down to this entry squared. And that looks like the following. This set of squared differences from from 1 up to n of these entries. And that should look somewhat familiar, right? If this was R3, we'd have 3 of those squared differences. In R2, the distance between u and v, or we can think of u as a point in the plane and v as another point in the plane. This is our distance formula. The first entry minus the first entry of the first point minus the first entry of the second point. Second entry of the first point minus second entry of the second point. Square them both, add them up, take the square root. That's our old Euclidean distance formula from the plane. This is just generalized to Rn now. So that's nice that things are consistent with what we might have known in the past. Now, we can use the idea of length to get at the idea of orthogonality. So orthogonality is really perpendicularity. So for two vectors u and v in the plane in R2, and really if we think of any two vectors u and v, we can think about the plane that those two vectors live in, so to speak, right? They form a plane together. So even if they're in R5, two vectors, we can put their initial points together and say that this is now whatever plane that they form together is maybe we just project down to that space and deal with that. Only we could make the same argument in any dimension if we like, because two vectors form a plane together. Nonetheless, we'll just consider this in the plane for now, and it really wouldn't change the drawing or how we think about it, but we'll fix it to R2. So these two vectors u and v are geometrically perpendicular if the distance from u to v is the same as the distance from u to negative v, right? If we bend that vector u a little bit to the side, well, then its distance from u to v is different from its distance from u to negative v. So this is a nice geometric interpretation of perpendicularity, and we'll use that to motivate a characterization for u and v being orthogonal. So remember that the distance from u to v is this. It's the norm of u minus v. And the distance from u to negative v is the norm of u minus negative v. Now I've squared both sides. That's a little odd, but we'll address that real quick. If these two highlighted squares aren't there, then these two norms are equal to each other in this way. And that's what I was actually arguing geometrically. But if we square both sides, this should still be true. So this would be implied by that. And if we only take positive square roots of these squared norms, which is what we set aside all the way back here, take the positive square root of these, well, then we'll have the exact same conditions. Yeah, we'll get the exact same equation. So squaring this really just makes it easier to compare both sides, right? We'd have a positive square root on the other side that we'd have to handle within our work here, and everything would come out the same if we did so. So u minus v dotted with u minus v, and this one comes out to actually the norm of u plus v squared, which is u plus v dotted with u plus v. Really, very formally, there should be a dot between this, so we know that we're doing a dot product of vectors. Now, on this side, something that the distributive property and commutativity allows us to write this norm as that, as the expression we have here. On the right-hand side, similarly, we get this expression, and we notice that u dot u and v dot v are common to both sides, so we subtract that from both sides. And we have negative 2 u dot v equals positive 2 u dot v. Divide by 2, and we get negative u dot v equals u dot v. Add u dot v to both sides, and we have 2 u dot v on the right equals 0 on the left. And that's written in reverse down here. 2 u dot v equals 0. Well, that's the only way for that to be true is if u dot v is equal to 0. So what we arrive at is this situation. So we'll define two vectors u and v and Rn to be orthogonal if u dot v is equal to 0. In other words, if their inner product is 0. Now, this is probably still somewhat familiar if you've taken a calculus course or potentially a physics course that's dealt with vectors like this. And we'll see even further discussion of this perpendicularity or orthogonality, one of these conditions by the end of the section that might be familiar to us from the past. So two vectors u and v are orthogonal if and only if this identity here holds. U plus the vector v, the norm of that sum is equal to the norm of u plus the norm of v. So, well, how do we know that that's true? So here's a sketch of that proof. So u plus v norm squared is this dot product, which when we multiply all that out, remember it's u dot v and v dot u, but v dot u is equal to u dot v. So we have two u dot v's, same work that happened up here. And then we have u dot u and v dot v. Well, this component is 0, right? If this component is 0, then u dot u is v dot v, and we have the right-hand side of this equation. Well, what's the condition for, and this is true if and only if u dot v equals 0, well, u dot v equals 0 means that u and v are orthogonal. So this is true if and only if u and v are orthogonal, and that's exactly what the theorem's telling us. So we have one identity to spot whether or not two vectors are orthogonal to each other. So we get another tool aside from the inner product to help us do that. Now, let's get into something a little bit deeper, and we'll talk about orthogonal complements to spaces. So if a vector u is perpendicular to every vector in a subspace W of Rn, then u is said to be orthogonal to W. So W is some subspace of Rn, and then if we find some vector u that happens to be perpendicular to every space in W, then yes, we've got a, and then we'd say that u is orthogonal to that subspace, orthogonal to all vectors. Down below it, just for a quick drawing of that, here's a space as a plane with vectors v in it. And if we have u, a vector that's perpendicular to this plane, well, then U is perpendicular to every single vector in that plane. So U is a part of the orthogonal complement to that plane. So it's an element of it. Now, any element along this line, which we'll call L, is actually a member of the orthogonal complement of W as well. So if we want to talk about orthogonal complements, well, we should define that. The set of all vectors that are orthogonal to W is called the orthogonal complement of W, denoted W perp, we might read. So I think I jumped the gun on using that term, but we see here then that this line L, for every vector that's on this line, U and all of its multiples, scalar multiples, are perpendicular to all the vectors in W. So L is actually the orthogonal complement of W. And likewise, any vector V in this plane is perpendicular to all the vectors L or U on our line L. So W is also equal to the orthogonal complement of L. So each of these two subspaces are perpendicular to each other. Now, so far, this is just abstract and not really connected to anything we've done, but on the next page, we'll see something that ties it all together with things we've worked on in the past. So our first theorem regarding orthogonal complements is the following. If X is in W perp, or X is in W perp, if and only if X is orthogonal to every vector in a set that spans W. So we don't need to check every vector in W. We just need to check every vector in the spanning set of W to see whether or not X is perpendicular to W. So to prove this, we show that, or we assume that X is in the orthogonal complement to W. So we're going in this direction. We're assuming we're doing the only if, right? X is in W perp, only if. So then we're gonna show that that implies that this statement's true. X is orthogonal to every vector in the set that spans W. Well, if X is in the orthogonal complement of W, that X is perpendicular to every vector U that's in W, or for every vector U that's in the spanning set of W. Since the spanning set of W are vectors that are in W and X is perpendicular to every vector in W, then yes, X is perpendicular to every vector in the spanning set of W. So that was the easy direction. We kind of get that one immediately. Now, if we assume that X is perpendicular to each U in a spanning set for W, and then for the sake of contradiction, we assume that there's a V in W for which X is not perpendicular to V. Well, then we know that the inner product of X and V is not 0, right? So 0 is not equal to the inner product of X and V, but X dot V, well, V has a representation among the spanning set of W, right? U1 through UK spans W. So there is some linear combination, some weight C1 through CK, such that the linear combination of U1 through UK is equal to V. So we replace V with that linear combination. And what we see is that once we carry out X with our distribution of the dot product over these addition signs and scalar associativity or scalar commutativity, we factor the scalar away from or out into the front of these dot products. Nonetheless, we do this K times, and we have C1 times X dot U1 all the way through CK X dot UK. But we know that X dotted with U1 is 0 all the way through X dotted with UK, because X is perpendicular to every one of these UI vectors in the spanning set, because that's what we assumed. X was perpendicular to all the vectors in the spanning set. So this has to be 0. But on the left-hand side, we have that it's not 0. So we have a contradiction. So that means that X must be perpendicular to every vector V in W if X is perpendicular to all the vectors in a spanning set of W. So going a little further and looking at this object, X dot, or sorry, not, a vector X being in the orthogonal complement of W, and investigating that if we take x plus y, two vectors that are in the orthogonal complement of W, then both of them satisfy this property. And their sums, once we distribute over a vector of multiplication, we'd see that x plus y is indeed dotted with, any vector v and w is going to be a member of the orthogonal complement. So it's closed under addition. Right? I don't have the details of this proof written down here, so I won't try to talk it through. It's a pretty straightforward proof, and you essentially use part one to help you with that, because you don't need to check every vector of v and w. You could just use the fact that if x and y are in w, the perpendicular or the orthogonal complement of w, then you just have to show that their sum is perpendicular or orthogonal to every vector in the span of it. And similarly for scalar products. Okay, to go on a little further, to tie it into something that we're actually familiar with. So this theorem tells us that A is an m by n matrix. The orthogonal complement of the row space of A is the null space of A. So this is something we've always sort of suspected. There's some kind of conservation here for m by n matrices in terms of their null space, row space, column space, and all of that. This somewhat similar to the rank theorem, which tied some things together, specifically the nullity and the rank of A being equal to, whose sum is equal to the number of columns of A, in other words, n. This one tells us even further about the spaces themselves and how they relate to each other. Now, the orthogonal complement of the column space of A is the null space of A transpose. So now we have an even better formed relationship for what null of A and column A and row of A, null of A all actually means. So in symbols, the orthogonal complement of the row space of A is equal to the null space of A. And similarly, the orthogonal complement of the column space of A is equal to the null space of A transpose. Okay, so in pictures, what that means is this. The row space of A is some set, and then the null space of A is some perpendicular subspace to that. Sorry, the row space of A is a subspace, and the null space of A happens to be perpendicular. The best we can do to show this, these spaces might be a little bit bigger than what we see here, right? In terms of dimensions, the null space of A in this case is one-dimensional, the row space is two-dimensional, one being a line and a plane respectively. We could switch them. The null space could be the plane and the row space could be the line, but nonetheless, if we're talking about three-dimensional space, both of these two spaces make up the whole space and they're complements of each other. So on the flip side, if we took the transpose of A, we see that the null space of A transpose is equal to the column space of A, or sorry, is the orthogonal complement of the column space of A. So all of these, so these spaces taken pairwise, or at least the row space of A and the column space of A, their complements are the null spaces of A and A transpose respectively. So let's prove this one. The second part follows a similar, essentially use the same proof as the book. The second part follows from taking A transpose and noting that the column space of A is equal to the row space of A transpose, and we could make the same arguments, and we could just use this result to finish that proof. So we'll use double inclusion. We need to show that one set is equal to another set. So first we'll show that the null space is a subspace of the orthogonal complement of the row space of A. This is not as complicated as it all sounds. So to do so, we let X, it's an inclusion proof, so we let X be in the null space of A, and our intention is to show that X is in the row space of A, of the orthogonal complement of row space of A. So in having done so, if X is arbitrary, then we can conclude that the null space of A is a subspace of row space of the orthogonal complement of row space of A. So if you've had Math 251 or another logic and proof course, then you're familiar with this inclusion style proof. So show that a set is a subset of another. You start with an element in the first set and then show that it must be in the second set for whatever reasons. So to get going with it, if X is in the null space of A, well, that means that AX equals 0, right? So the null space of A, X is some vector for which is a solution to the homogeneous problem. So A times this vector X is 0, which means that X is perpendicular to all of the rows of A. Think about it. The matrix product of A times the vector X is each row of A dotted with the vector X in this product right here. And for each of those row times this vector X products, we get 0 for every entry. So the dot products of the rows of A are equal to 0. So X is perpendicular to every row in A. So X is perpendicular to the row space of A. That means that X is in the orthogonal complement of the row space of A. Now remember too that we've only showed it for the rows of A, but remember that the row space of A, the rows of A, the linearly independent rows of A, form a basis. In other words, a spanning set for the row space of A, which means that X is perpendicular to the spanning set for the row space of A, which means X is perpendicular to all vectors in that space, as we saw in the previous theorem. And knowing that X is in the row space, or the orthogonal complement of the row space of A, tells us that the null space, since X is an arbitrary element, we now see that null space of A is a subspace of the orthogonal complement of the row space of A. It's a mouthful. Now, going the other direction. So we let X be an element of the orthogonal complement of the row space of A, which means that X is perpendicular to each row of A. If X is perpendicular to each row of A, then this matrix product is going to be each row of A dotted with X when we carry out this matrix product. And if X is perpendicular to every row of A, well, then each of those products, entry by entry, will be 0 on the right, which tells us that this matrix equation is satisfied by such an X. Hence, X is in the null space of A. Since X was arbitrary and started in this set, and we're able to show that it's in this set, this means that this set is a subset of this set. So now we've showed inclusion the other way. So in this situation, we have this set A is a subset of set B, and set B is a subset of set A. The only way that this can be true is if these sets are equal to each other. So there's our double inclusion proof with this scenario. But it makes a nice sort of tidying up and summary of what we've been dealing with all along, right? We've calculated null spaces, row spaces, column spaces, all these things. It turns out that they have this nice complementary relationship. Null spaces are perpendicular to row spaces. And then null of A transpose is perpendicular to, or orthogonally complementary to, the column space of A. In other words, they're two completely different subspaces, sort of disjoint from each other in a way. Now, for two vectors U and V and R, we've probably seen this formula before, but the angle theta formed between them, we have this result here. This comes from the law of cosines. So draw U and V arbitrarily in the plane, or wherever, really, right? Think about it in the plane, because two vectors just form a plane. They have an angle theta between them. Convert this triangle to, convert these two vectors to a triangle where we've closed the space between them with the line segment, which is actually the vector U minus V. And we've denoted the lengths of each side of this triangle in terms of our norm, our vector norm here. Now we know by the law of cosines that this quantity squared is equal to this quantity squared plus this quantity squared minus 2 times this quantity times cosine of theta. Right? All of that is written down below here. You just have to translate the law of cosines from the length values that we have in that triangle. Now write down what that means. This line here, and the rest of this is just mopping up the details. What you should arrive at once you simplify all this, is this formula here. So we see where it's yet another characterization of the inner product and how to deal with problems that might ask us to handle the angle between two vectors u and v. Note that if u and v have an inner product of 0, well, their magnitudes won't be 0 or necessarily 0, right? If u and v are non-zero vectors and they have an inner product of 0, and start with that maybe, then this is not 0. But the whole thing needs to be 0, so that means the cosine theta needs to be 0, which means that theta must be 90 degrees. In other words, u and v must be perpendicular to one another. This formula is very commonly used in multidimensional calculus and physics as well, and just generally in applied problems. So finish the details to that one, and that'll close up 6.1.